Welcome to this presentation. In this video, I'll walk you through the architecture, key features, and training process of a spot jamming detection net developed and implemented in our FreeScopes platform. This model is uniquely designed to detect the presence of spot jamming in radar data and accurately locate the true position of the target, even under conditions of intentional jamming. This type of model is crucial for air traffic control (ATC) systems, where ensuring accurate detection and localization of targets, such as aircraft, is essential for maintaining safety and operational efficiency. Jamming is a common electronic warfare technique that attempts to overwhelm radar systems with noise or deceptive signals, making it difficult to identify genuine targets. By deploying this model, ATC systems can reliably mitigate the effects of spot jamming, ensuring accurate target detection and classification, even in challenging environments. Let's start with the first figure, which provides an overview of the connected model in our platform. The workflow begins with the load input data block, which loads the recorded radar data and the corresponding position labels. These inputs form the foundation of the training dataset, allowing the model to learn how to distinguish between genuine targets and jamming signals. The data is then forwarded to the pre-process input data block, which prepares the radar data for further processing by performing several critical operations. Normalization of IQ data. The in-phase and quadrature IQ data from the radar simulator are normalized. This ensures consistency and reduces variability caused by external factors, making the input data more uniform and easier for the model to interpret. Feature extraction. Using the Welch method, the block calculates several advanced features from the IQ data to enable the model to differentiate between jamming signals and real targets. PXX, output of the periodogram. This represents the power spectral density, PSD, which reveals how power is distributed across different frequencies in the signal. It helps the model identify anomalies like jamming noise. Centroid. The centroid of the PSD indicates the dominant frequency, helping the model pinpoint regions where genuine signals are likely to appear. Bandwidth. This measures the range of frequencies occupied by the signal. Genuine signals often have different bandwidth characteristics than jamming signals. Entropy. Entropy quantifies the randomness or complexity of the signal, allowing the model to detect jamming noise, which typically exhibits higher entropy. SEX from the spectrogram. This represents the time-frequency characteristics of the signal, providing insight into how the signal evolves over time. It is particularly helpful for identifying patterns associated with jamming. Mean of IQ. The mean gives an average trend of the IQ data, helping the model assess the baseline signal strength. Variance of IQ. This measures how much the IQ data values deviate from the mean, highlighting fluctuations caused by jamming. Kurtosis, KURT of IQ. Kurtosis reveals the peakedness of the signal, which helps in detecting unique features of targets versus noise. Skewness of IQ. Skewness measures asymmetry in the IQ data distribution, capturing subtler imbalances caused by jamming. These features are vital for enabling the model to distinguish between legitimate target signals and the effects of spot jamming. Additionally, the position labels are transformed into Gaussian labels, which smooth the position information and help the model localize the true target position despite the interference caused by the jammer. Once the pre-processing is complete, the data flows into the model, which has been carefully designed to perform two critical tasks: detect the presence of spot jamming and identify whether a genuine target exists. Accurately localize the true target position even in the presence of jamming signals. The model follows a structured architecture. The first layer is a one-dimensional convolutional block with a kernel size of 20 by 1 by 16, 16 biases, and a ReLU activation function. This block extracts spatial patterns from the radar data, identifying features indicative of genuine targets versus jamming signals. The output is passed to the flatten block, which reshapes the features into a 1D vector. The dense block with 256 neurons, 256 biases, and a ReLU activation function learns higher-level representations from the flattened data. From here, the data is split into two branches, corresponding to the model's dual tasks. Localization branch This branch flows into the position input block, which has 64 units and a ReLU activation function. It then connects to the position output block, which contains 400 units with a softmax activation function. These 400 elements represent a resolution of 0.05 meters, covering a range of 20 meters. The softmax output provides a probability distribution across all positions, with a spike at the true target location, allowing the model to accurately localize the target, even under jamming conditions. Detection branch. This branch flows into the detection input block, which has 256 units and a ReLU activation function. It then connects to the detection output block, which contains 1 unit with a sigmoid activation function. This single output performs binary classification to determine whether a target is present, class 1, or not, class 0. This design enables the model to simultaneously detect spot jamming and locate the true position of the target, ensuring robust performance in radar-based target detection for ATC systems. Now, let's turn our attention to the third figure, which shows the model architecture in greater detail. To recap, the ConV1D block extracts spatial features with a kernel size of 20 by 1 by 16 and a ReLU activation. The flattened block reshapes the features into a 1D vector for dense processing. The dense block learns high-level patterns with 256 neurons and a ReLU activation. The two branches then handle localization and target detection separately. The position input block connects to the position output block with 400 softmax activated units for accurate localization. The detection input block connects to the detection output block, which has 1 sigmoid activated unit for binary classification. Finally, in the second figure, we see the Python console displaying the model training process over 10 epochs. You can observe the following trends. The loss function decreases steadily with each epoch, indicating the model is successfully learning to minimize errors. The accuracy improves as training progresses, reflecting the model's growing ability to detect targets and mitigate the effects of jamming. At the end of training, the console also shows a confusion matrix, which evaluates the model's performance in detecting targets under jamming conditions. The matrix provides a clear picture of how well the model differentiates between genuine targets and jamming signals, demonstrating its effectiveness in real-world scenarios. In conclusion, this spot jamming detection net is an important advancement for air traffic control, enabling reliable detection and localization of targets, even in challenging conditions where jamming signals are present. Thank you for watching this first part, and in the next part, I'll demonstrate the model's deployment and real-time performance. Stay tuned.